All right, as I said, our next speaker is Sungwoo from Chicago and Oregon National Lab. Please take it away.
Thanks. Thank you very much. For my opening remark, let me just copy Offrey and paste. Thank you, organizers. So today I want to talk about axion theory, very simple axion theory, especially cosmic string in those theories, and ask what happened if I couple that theory to a sector of somewhat non-trivial or less familiar kind of field theory, which is topological quantum field theory. You might wonder where they come from. That's the goal, how to explain that. All right, let's get started on this. So I want to start my talk with a maximally trivial statement. Okay, so symmetry, we all know and agree that has played very important role in all areas in theoretical physics, right? In particle physics, formal field theory, gravity, string theory, condensed matter theories. And in recent years, like last decade or so, the notion of symmetry has gone through, to my mind, explosive generalizations. Here I'm just showing a couple of those direction of generalization. Unfortunately, I won't have time to go through one by one, but I'm very happy to chat about each of these in the rest of my talk. But for now, I just want to make a quick comment about this because I'm going to be speaking of a little bit of this language today. So the first type of generalization is that in usual sense, traditionally, we think of the symmetry acting on particles, right? Particle is a zero-dimensional object. And so a symmetry acting on a zero-dimensional object is called a zero-form symmetry. It acts on the local operators, all right? Then there is a generalization called the higher form symmetry, where, for example, one-form symmetry, as you now can guess, acting on one-dimensional object, so line operators. And then likewise, two-form symmetry acts on, say, two-dimensional object, surface operators. And one of the example of, for example, two-form symmetry and whose charged object is cosmic string, because it has a string which is one-dimensional, and then you travel in time that looks like a two-dimensional object. Okay, so therefore, one of the important symmetry of two-form kind is the one that acts on the cosmic string. Okay, so as a particle physicist who's also getting excited about this recent development about the symmetry, here are the questions I want to raise and hopefully address some of them. So first question is whether there exists a four-dimensional quantum field theory relevant in particle physics that enjoys the generalized symmetries. Okay, pretty obvious question. Second point is whether if I find such a theory, which I will, otherwise I won't keep this today, whether there is observation and implications which is associated with or at least related to those existence of generalized symmetries. Okay, so I want to see whether generalized symmetry can do something non-trivial interesting in particle physics. And ultimately, I'd be very excited to see if generalized symmetry can do something in a non-trivial job in addressing important problems in particle physics. All right. So today I will be mostly focusing on the first two kind, but then certainly I've been thinking about this question. I'm pretty positive that there might be a good answer to this question. But for now, let me just focus on these two questions. Okay. So that's the goal. So how am I going to answer these questions? So here is the outline of the rest of my talk. First, I will introduce you a very, very, very simple theory whose theory action you have seen at least more than one time throughout this workshop. So that is an axion coupled to Maxwell theory. And then I will couple this theory, very simple theory, to a sector of a topological quantum field theory, which I will explain what I mean by that. So I will introduce two different ways of doing that. And then I will go through what will be the observational and possibly some of the theoretical implications of those terms. Okay, and then I will go. Okay, so what is axion-Maxwell theory? I really mean by this. Okay, here is axion, which is the Goldstein boson of a U1, which is spontaneously broken. And then there is a gauge sector, which is U1. Here I'm taking to be U1. And then there's just a Chern-Simons interaction between axion and then gauge field with the discrete coupling constant K, which needs to be integer in order for axion to satisfy correct periodicity. Just to simplify notations for myself, I will just use a differential form notation about each of this. Basically, this means that if you are not familiar with, F is a two-form field, which means that it has two antisymmetric indices, as you see here. And then this product, called the wedge product, take the two-form object and then just smash it together to generate another form object by maximally antisymmetrizing all the indices you have. And here's another kind of thing. So there's a wedge product with a star. So for the purpose of today's talk, this just means that you contract all the Lorentz indices. Okay, so I'm going to be using this notation, and that's all you need to know for today. This very simple theory, I'm sure you agree, enjoys a large class of generalized global symmetries. It has a 0 form, 2 form, 2 1 form symmetry. In fact, these different kind of high form symmetries mix up together in a very non-trivial way to construct the mathematical structure called the tree group. I won't have time to go into, but I'm very happy to talk about it. And very recent days, it was even shown that this theory also has what's called the non-invertible symmetry. There's a symmetry acting on the particle, and also line operator, which does not commit inverse operation. So that's why it's called the non-invertible symmetry. But nonetheless, the point is that this theory, very simple theory, has many different kinds of generalized global symmetry. For the purpose of this talk, again, I won't have time to go through each of them, but our paper will have a very detailed discussion of every single aspect of this thing. But I want to just go through the first two, okay? Zero form axion symmetry, which means that this zero form symmetry acts on the local operator, right? And here, that local operator is the axion field. So shift symmetry means the axion shift by constant amount. That's what I mean by zero form axion shift symmetry. The second one is a two form axion winding. I already mentioned that two form symmetry acts on two-dimensional object, and that object is the axion cosmic string. Okay, so I can write down a surface operator, okay, localized on the axion string worksheet, and on that thing, this symmetry with this charge, which is basically axion winding number, acting on, and it measures the charge of this two-dimensional object. Okay, so that's the two form, and mostly I will be using these two symmetries today. Good. Yes, that is a ZK is broken down to the ZK, and I will even do further funny thing on top of it. But yes, we start with the ZK. Great. Okay, so with that, let me now introduce the first TQFT coupling, which means I take this very simple theory, local quantum field theory, and couple it to a sector of topological quantum field theory. So here is the sector. So here is the sector A, axion, and U1A gauge field. And then I want to couple it to ZK, Zn, sorry, the topological quantum field theory. So this is original action I introduced to you with the coupling constant K. And I just want to introduce a label so that I call this sector to be A sector. So I just added a subscript A. And then I want to call this sector to be B sector. So it's very easy to keep track of. So here is the full action that I want to study. So the action that describing this TQFT sector or topological quantum filter sector with these two topological degree freedom looks like very simple action of this. Okay, you might wonder where they come from, you might be very familiar with it, but I will talk about this in the next slide. So let me first focus on interaction between the two. Okay, so this sector has a one form field B1 and one two form field B2, and then I'm going to be using notation that FB means that basically field strength of this one form field B1. So now the coupling between the two sector looks like basically a copy of this stuff, right? So there's an axion, one factor of a field strength from the A sector, and the one factor of a field strength from the B sector. So that's the one coupling, local interaction. And then obviously you can generalize this thing to axion coupled to two factors of instanton density or two factors of field strength from this sector. Okay, very simple and intuitive, and you can imagine write down this trivially. And then I just call the coupling constant for the first kind to be KAB because there's A and B. And the second one I call the KB because of BB, and then there's a KA. Okay, hopefully the notation is explicit. Okay, so I didn't explain to you what is this and why that is the Zn topological quantum field theory. So let me just briefly explain to you that. So claim is that this action describes discrete, particularly Zn gauge theory called the BF theory. There are two reasons why this is called the BF theory, but that's offline conversation. I think the easiest way to show this is actually A, topological quantum field theory, B, non-trivial, C, it is actually Zn gauge theory. I think the best way to see that is derive this explicitly from mundane abelian Higgs model. So you start with a U1 gauge theory. There's a Higgs scalar who had a charge n. The physics we all know, right? Starting from U1, there's a charge n scalar, you break it down to the Zn, right? There's a remnant of Zn factor. This is the action. This is that action. And this scalar phi is not the entire scalar field, but it's an angular variable. Okay? So you see, there's no phi appearing here. So this is the action of abelian Higgs model. Already I Higgs down to with the charge n. Okay. Now let me focus on this cross term. So there are two terms, right? There's this guy, that guy, and then the other one. So if I being sloppy, just write down one of that, it looks like this. Okay, so this d phi, which is the one form, I can dualize using Haji-dual operation to get, if I call this electric description, I can dualize to get magnetic description. But setting aside the technical detail, if you do this, you get the three form object, which is d times v2. So if I use this relationship, plug it back here, you already get n times v1 wedge dv2. And then if I put correct normalization, you get this. Okay, so I already gave you two ways, right? A, physics-wise, I already know what I should expect from this action because I kicked down to the Zn. And B, I just explicitly shown you that if I do that, I get this action. Therefore, this corresponds to Zn discrete gauge theory. Okay. Now, you might say, okay, what is this? Why is this topological? A, this action doesn't involve any metrics, so topological. B, more importantly, this action does not come with any propagating degree of freedom, right? This has only one derivative in it. So it looks like a Lagrange multiplier action. In fact, you can derive equations of motion trivially, and the result is that you're setting field strengths of each of the terms to be 0. Okay, so there is no propagating local degree of freedom. It doesn't have a metric, so it is a topological quantum field theory. Nonetheless, it is not empty. It is not empty because, first of all, this theory admits interesting gauge invariant operators. So first of all, here I'm showing you a gauge invariant Wilson line operator by integrating one form field along one-dimensional manifold. And then I'm also here showing you two-dimensional or a Wilson surface operator by integrating V2 over two-dimensional manifold. Okay, so there are Wilson operators, and in particular, they satisfy non-trivial correlation function, and it is classified by Zn phases. So it describes basically a phase with a topological order, and there is this non-trivial information data encoded in this theory. So it is a TQFT, but yet non-trivial. Okay, so hopefully this gives you some of the glimpse that yes, I'm actually talking about TQFT with a non-trivial information with it. All right, let's get back to the original theory. So here is the action that I wanted to study again. So A sector and the B sector and coupling between the two. All right, again, the question was whether A, there is IR universal observable effect because of these TQFT couplings. What do I mean by IR universal? I just mean that any observable consequences which is insensitive to the details of UV completion, okay? So I want to study the effect just coming from this thing without needing to specify any UV information. That's what I mean by IR universal. And also more importantly, you might wonder, I never seen this type of thing. Is this very exotic or pure academic setup? But then we will show explicitly in our paper, although I won't have time today, this can come from very mundane standard QFT, okay? Just coming from very minimal extension of a KSVG, you can get this. Which means that if that is true, if you believe me about that point, I think that point illustrates the importance of studying carefully the effect of discrete remnant or this TQFT remnant coming from very standard TQFT. Otherwise, we will be misleading in terms of what observable we should expect. Okay, so I won't have time to address this question, but I'd be very happy to discuss offline. But mostly, let me just try to answer this first. So, IR universal observable consequences, and that can be understood by means of anomaly physics. So you might not be either not familiar with it or you have forgotten some details. So let me just briefly review to you the basics of anomaly inflow without TQFT coupling. So this is actually without TQFT coupling, and this is a lazy poor theorist version of closing string network in the space box of space and time. Hopefully you get the picture. And then let me just zoom in one of those guys, and then let me represent that with this picture. Okay, so here is the action string, a little bit zoomed in, and then the charge of this guy will be measured by axion winding. And then, for example, let's consider winding number 1 object. Okay, don't call me this wormhole. This is my lovely action string. Okay, because someone. Anyway. So this is my action string. You will see this picture again and again and again. This is a action string. Okay, let's move on. So what is anomaly inflow? Anomaly inflow is the statement that this very nice looking action secretly is not gauge invariant if I insert action string singularity in the space and time. So the point is that without having a lot of time to discuss, but this one is not U1A gauge invariant. In fact, you can show pretty quickly that the variance under the U1 gauge transformation looks like this. So let me just zoom in that expression, explain the physics of it. So A, this delta function is basically saying that this is 0 everywhere except action string worldsheet. Okay, so therefore, gauge violation is localized on the action string worksheet. That's not fact number one. Fact number two, if you look at this, the size of a violation goes like f over 4 pi, which is a two-dimensional chiral anomaly with proportionality factor k, which came from this k. Therefore, this is the anomaly coefficient of two-dimensional chiral anomaly. Okay, so that's fact number two. Now, in order to restore gauge invariance, otherwise we are dealing with the Sick theory. In the presence, once again, in the presence of action string, therefore, I had to cancel this gauge violation by introducing a two-dimensional quantum field theory localized on the action string worksheet, which is also anomalous. Okay, this is a general feature of anomaly inflow. You have a Sick theory outside, you have a Sick theory inside, but they make a good friend and then live healthily. Okay, so that's the idea of anomaly inflow. Now, this is a very intuitive and physical picture in terms of current as well. So I won't have time to go through this detail, but basically, if you believe me, exactly this physics that I just described to you can be rephrased as follows. I take my action string with the winding, which is measured by gradient of axion, and then somehow imagine that this guy is traveling in the background electric field. Okay, and then one can show by using this expression, Pauli current, that this triggers current, which is marching towards the core of action string. Okay, and if we had a notion of continuity of the current, it cannot just stop there, right? It should keep going. And that means that there should be current going through the action string, which is indeed a superconducting. But the existence of superconducting current through the action string means that there must be charge carriers in there. But those set of fermions, two-dimensional chiral fermions, which is equivalent to the boson in 2D, is anomalous set. It has its own two-dimensional gauge anomaly in such a way that that gauge anomaly cancels. I think cancels the Burke problem. Now let's do the exact same exercise with this in the presence of a TQFT coupling. Now let's first look at the variation with respect to U1A. I have a U1A field here, U1A field here. So I will get two terms. One proportional to the Ka, the other proportional to the Kab. I can do the same thing. Now I can vary the same action with respect to Zn gauge transformation. Again, there is a B here, I will get two terms. What's the physics of this? So talking about first U1A gauge transformation, once again, there are two terms, but the first term basically means that I vary the action with respect to U1A, that it is proportional to the Fa. So this corresponds to the U1A squared to the anomaly. Therefore, there must be charge carrier charged under U1A. B, the second one, which is introduced because of TQFT coupling, say that there is also mixed anomaly between U1A and Zn. Therefore, two-dimensional theory with the fermion now also must carry extra quantum number in order to match out or cancel out this mixed anomaly. So the physics in terms of current, therefore, is that if action string passes through a background electric field, because I'm talking about U1A variation, it triggers a current. It carries U1A charge, but it also must carry Zn charge. So I modified the 2D quantum field. They're localized on the action string, right, explicitly. So I literally changed the quantum numbers of those fermions. If I do the same exercise with respect to Znb transformation, again, there are two anomalies and the same thing. So now if I take my action string, it travels through Zn background because I'm talking about Zn variation. Again, it needs to turn on the superconducting current with fermions or bosons, which carry both charges with the proper anomaly coefficient. So to summarize in the first part of the talk very quickly, second part is short. Don't be panic. Is that without a TQFT coupling, this is the amount of consistency condition. This is the regular standard picture. In the presence of TQFT coupling, first of all, I tripled the amount of consistency condition in the theory, two-dimensional quantum field theory. And as a result of that, we get this picture. But in particular, now this is exciting to me in a way that there is more than one way to turn on the superconducting current along the cosmic string. And I believe this might have interesting phenomenological application, which we are really thinking about. All right, with that, just not to panic too much, our organizers, let me move on to the second one. Hopefully that's shorter and quicker. So the second TQFT coupling, I do somewhat exact looking thing to you, but I'll show that I want to gauge. I said that there is action shift symmetry, which is 0 form, right? And then I want to gauge discrete subgroup of that thing. Okay, starting with global symmetry, I want to gauge it. Here the claim is that gauging a discrete subgroup is equivalent to coupling the original theory to a sector of TQFT. How do I see that? So let's start with the very mundane picture first. So suppose I have theory of the global current J, usually what we do as a quantum field theory is couple that to the background gauge field, use that as a source, right, for the current. But now if I decide to gauge this guy, this now has to get a life. All of a sudden, of course, this becomes dynamical. There should be kinetic for that guy. There's a sector of gauge theory. And that original A mu J mu turns into the coupling between the two sectors. Okay, so let me do the same thing. Here is the action for axion with the shift symmetry. And then I claim that this is the consistent action that is like a coupling action shift symmetry to a background gauge field, here currently A. Okay. So now what's the picture? If I gauge this guy, but this is the gauge field, now this will turn the gauge field of a Zm gauge theory, right? So I should have this picture. All of a sudden, if I gauge, there's a sector of a Zm topological quantum field theory, and then there's already a sector, and then the coupling now is basically becoming a coupling between the two sectors. So once again, therefore, gauging a discrete subgroup basically turns the picture of coupling original theory to TQFT. Now, I want to just briefly, quickly explain to you what is the most exciting feature of observational feature of this operation. So what happened to the original action string? Okay, so full analysis can be carried out by understanding mixture of anomalies among all these higher form symmetries, the special understanding of breaking of three groups. But I won't have time, so let me just give you a very quick way of understanding this. Okay, maybe.
Go ahead. Don't worry about it.
This good, very good. That's how you want to make a friend. Okay, so for that, let me just note that action string is a two-dimensional object, right? String, treble, two-dimensional object. And in this language, this is a 2D defect charged under two-form U1 global symmetry. Okay. Now I can construct the current for this one, which I can just claim for now to be that it is a proportional to the dA, okay, derivative of axion. Okay, and then I can construct the charge by integrating this one form field along the one-dimensional manifolds. This is a charge for U1 two-form global symmetry. And then I can construct the group element by just exponentiating this object with the alpha primer. Okay, this is transformation primer, alpha as usual. Okay, here's my charge operator for the two-form U1 symmetry. Now, the fact that action string is charged under this symmetry just means the following expression. So let me just quickly explain. So V is the surface operator describing action string, axion cosmic string, okay? I'm just Wilson operator integrated over action string worksheet with winding number M. That's what this means. And then I can measure the charge of this guy, which means that the winding of this guy by acting this guy with the group element. And if the sigma 1 has a non-trivial linking with this string worksheet, as also introduced, linking, meaning they have to be related somehow, right? Otherwise, how this thing knows about this thing at all? So there should be some relation among them. Then it picks up the phase which knows about the linking or winding number of this object. In other words, charge of this object. Okay, so that's what I mean. Now let's do the exercise. What happens if I gauge Zm subgroup of action shift to symmetry, which started with Zk? For some reason, I didn't have time to. So what is the impact? We gauged it, which means that axion goes to 2 pi over m, which is a Zm transformation, is not gauge transformation. And every global symmetry operation must be gauge invariant. Okay, we cannot ask a correlation function among the gauge non-invariant object. So then you can ask, what is the constraint on this transformation parameter alpha? Because of this gauging feature, you found that the alpha is equal to 2 pi m of Zm is only allowed. This is only good global symmetry operator. Now you can do the Gedanken experiment, okay? Suppose you had action string and there's some random winding number, which we don't know exactly. Suppose you try to measure the effective winding by using only well-defined operators. And then the phase always comes out to be proportional to integral multiples of m of Zm. So whatever you do, you conclude that, oh, I only get action string whose winding number is always integral multiples of m. So what's the picture? We start with this picture. So y-axis is the string tension, and then x-axis is the charge, meaning action winding. Okay. Before gauging, we started with this picture. So there was some Topological symmetry breaking where action string is born. You expect that every integer value of the winding should be expected. Now, if you gauge that, I just showed that all of a sudden, boop, everything's good except the ones that has the integral multiples of that. Okay, so this is a first modification. And ask, oh, what happened? Where did other good things go? Okay, the answer to that question can be understood by noting two facts. A, we decide to gauge a symmetry which was already non-linearly realized. Remember, axial shift symmetry comes from U1 phase rotation when it is broken down spontaneously, right? So we gauge the spontaneously broken symmetry, but this is usually the scale, the original scale where that non-linear realization happens. But how can I gauge before that if such a non-linear realized symmetry already exists? Okay, which means that in order to be able to gauge such a symmetry, there must be another scale higher, which already prepares non-linear realized global symmetry for you. Okay, so this is a picture number one. Picture number two, now I gauge it. So let's recall what happened to the U1 gauge theory. So take the global U1 symmetry, you spontaneously break it, you get Goldstone boson. Great. Now, if you decide to gauge the U1, what happened? This physical nice Goldstone boson becomes gauge degree of freedom, right? And you call it a longitudinal mode. Here too. So we started with a global string because it comes from the spontaneous broken global U1 symmetry. I gauge shift symmetry. It affects in detail each dual symmetry, which is two-form symmetry, and it turns those Zm amount to be local string. All right. So what happens is that once you gauge it, all those Zm amount of cosmic string that turns into strings of a BF theory, which corresponds to Zm, topological quantum field theory. So the picture overall is that before was this picture, you explicitly modifies to this picture. And I mean, it's a futuristic, or in principle, if we can carry out action string spectroscopy, we should be able to tell which one we are talking about by measuring the energy density a bit. So with that, let me quickly conclude. I believe that non-trivial TQFT coupling, or in general, topological modification of a local quantum field theory we love, can lead to very exciting, interesting, and important observable consequences. Okay, and understanding physics of those modifications or implications, I believe that generalized global symmetry and their anomaly play extremely important role. Okay, so also more importantly, I believe this is just the beginning. Especially, what are the generalized global symmetry in particle physics? What might be the observation and consequences of that? And here, let me just leave my slide with that. But I think this is very exciting to think about this question. With that, thank for your attention. Thank for the organizers for generosity of
One quick question. Semi-quick question.
Go to somebody else. How do you turn on Zn background in the early?
So very good. Good. So this can be okay. So one of the applications we've been imagining is that suppose dark matter is only coupled to us through the topological for Zn, which means it carries Zn thing. And if you look at the very dark matter heavy environment, but with very little baryonic activities, there will be Zn turned on. Okay.
Okay. That's
No. Suppose that this action string passes through that. I show you that Zn can turn on superconducting current, which is a simultaneously U1 ENN current. So all of a sudden, this can attract the charged object towards the action string, even though I knew that there's no electromagnetic field, and it can possibly create an electromagnetic signal out of it. Anyway, so that's a quick bit idea we had about it.
it's better than that. We can set the axion relative density. Let's talk about it.
Yeah, very good. Okay.
Let's postpone the further discussions for after.
Cool.
Great.
Thanks a lot.
Thanks, Sungwoo.